Hello there. My name is Johnson Makmot, Kabira, and software engineering from Group 47. And I'm going to be taking us through our project. This is an explainable edge optimized ensemble architecture for microfinance credit scoring under synthetic data constraints. Yeah, so this is our project, and let's get straight started. So these are the contents of our presentation, which involve the introduction, related work, problem statement, research questions and objectives, research contributions, methodology, system architecture, dataset description, results, conclusions, unspecified limitations, and counter-action plan, references, and acknowledgement. So our background is we know that credit access is essential for individuals and businesses. So we have traditional methods which are slow, inconsistent, and prone to manual bias. So we decided to come up with this machine learning system which is used for predicting loan repayment. So our core metrics are based on using credit scores and financial indicators. So our project significance is to promote smarter lending and financial inclusion. So this is important because it reduces financial losses and default rates and speeds up automated loan approvals. So our related works and recent trends, we know we are shifting to advanced models and transitioning from traditional statistics to machine learning algorithms. So we have to performers whereby recent studies prove that ensemble methods like XGBoost and random forest achieve high accuracy in default prediction. So we came up with our model which uses explainable AIs, which helps on heavy research focus using Sharp and Lime to ensure model transparency and regulatory compliance. So also have data imbalance, whereby modern techniques focus on resolving class imbalance. This is where they are defaults versus repayments. So our domain application program is inefficient evaluations whereby traditional manual loan assessments are slow, they are inconsistent and highly prone to bias, and also the information gap. This one involves many loan applicants who lack this extensive credit history. So this one makes manual evaluation inaccurate. So a business impact is financial institutions face the high risk of loan defaults and financial losses without reliable risk assessment methods. So our computational problem is we have the algorithmic need. Here is how to build a predictive model that analyzes diverse borrower information to find hidden behavior patterns. So binary classification also allows mapping multidimensional financial features like income dates, age, uh, to a specific target variable. So here it shows whether someone is likely to repay, which is low risk, or likely to default. So data processing, this involves a technical challenge of handling missing values, encoding categorical values, and modeling synthetic or historical datasets. So our research questions and objectives, we have the special objectives which are to collect and analyze key financial behavior features such as credit scores and income from synthetic borrower datasets. Then we also want to develop and train machine learning classification models, random forest, XGBoost. Then we also want to evaluate performance of the trained models using metrics like accuracy, precision, recall. So we also want to design an automated risk scoring mechanism that provides data-driven repayment predictions for new applicants. So those are our specific objectives, and also how can this machine learning classification model be optimized to reduce bias and produce explainable learning decisions. So in this case, we want to generate and pre-process synthetic borrower data that accurately presents applicants with limited credit histories. We also want to train and optimize classification models like random forest, XGBoost. Then we also want to evaluate transparency and fairness by integrating explainable AI tools like Sharp and Lime. Then also want to design automated explainable risk scoring mechanism that provides data-driven, interpretable learning decisions. So we generate a specialized synthetic borrower dataset to safely model financial behaviors and accurately present applicants with limited credit histories. So developed a robust machine learning classification models like random forest, deployed novel explainable AI pipelines using Sharp and Lime. Then we built an automated explainable risk scoring mechanism that delivers data-driven, interpretable loan approval decisions. So our research methodology have algorithms like logistic regression, which is the simple baseline, had decision trees, which involved visual decision logic, and random forest, which involves ensemble method and high accuracy. We had gradient boosting for XGBoost and neural networks for large data sets. So a system workflow is a data collection, cleaning, pre-processing, feature engineering, model training, evaluation, and deployment. So here we have an applicant who enters their inputs, their information could be the credit score or monthly income or loan amount. Then it will pre-process where there's the data pre-processing. This one handles the missing values, encodes categorical data, it normalizes numerical data, and calculates the DTI ratio. Then the machine learning aging, this one's like random forest and XGBoost. This one just compares the applicant's data against his historical patterns. Then the decision output is whether to decide a repayment prediction, also calculate the risk score and probability of default, of which after it displays on the dashboard to show the final decision whether you're going to approve this person or reject them. So this is the model architecture and mathematical foundations. So we have the logistic regression, which serves an industrial baseline, and that was its calculation or mathematical method formula. Then also the XGBoost, which is highly optimized implementation of gradient boosted trees, and we also deduced that formula out of it. Then we had the ensemble machine learning method that constructs a multitude of decision trees during training and outputs the model, the classes, and effectively captures nonlinear relationships. That's also its formula. Our data set, we since we could not get most data sets from banks and other sensitive uh, entities, since they were protected and they could not easily share their data, we decided to come up with our own data set. It's a synthetic data set, and we created it using a synthetic agent, which is rule based and statistical to ensure privacy. So it has its core input features like credit score, monthly income, loan amount requested, employment status, existing debts, payment history, age, debt to income ratio, number of previous loans, and also a target variable is repayment outcome to whether this person will repay or default. Then we have our data processing steps, which handles missing values and encode categorical values. So these are just some of the output from our exploratory data analysis. Where I have the bivariate analysis, we have the feature correlations, repayment status, and the invariant analysis. So we plan on implementing some new features onto our project to make it stand out. And these are some of the features whereby we have some most complex features like social network trust graph, uses trust graph neural networks to analyze borrower relationships. We have the temporal financial stability modeling. This one uses time series analysis to track financial trends over time and analyzes income trends, spending patterns, and debt growth. Then we have the highly complex core models like fraud risk detection layer, identifies suspicion loan applicants before scoring, and uses anomaly detection techniques such as isolation forest or autoencoders. We have the stacked ensemble model, combines multiple models like logistic regression, RF, random forest, XGBoost neural networks. Then we also had explainable AI, which uses sharp and line. This one allows you to explain the reason why this person is not going to be given a loan or is going to be rejected. Then shows also which features contributed the most to the decision. Then we have some more advanced risk analysis, which involves dynamic risk scoring and monitoring, which continuously updates borrower risk scores after loan approval. Then detects spending spikes, income drops, or missed payments. Loan stressing testing simulation simulates economic scenarios such as income loss or interest rate increases. Default probability forecasting predicts when a borrower may default. Then we also have fairness and bias audit. This one detects discrimination in the model across demographic groups. We have behavior credit scoring, uses financial behavior instead of traditional credit history, and analyzes mobile money usage, spending volatility, and saving patterns. Then we have a macroeconomic sensitive index, measures how economic conditions affect the borrower risk. Then have segmentation, which are whereby borrowers are segmented into different risk profiles using clustering algorithms. We have some features like psychological risk indicators, analyze borrower behavior during the loan application process. Geospatial risk profiling uses geospatial data to analyze regional financial risk patterns. Borrower financial resilience score measures a borrower's ability to survive financial shocks. Dynamic risk segmentation classifies borrowers into risk tiers, low, medium, high. AI-driven personalized loan recommendation suggests optimal loan amount, interest rate, and repayment terms. Then our deployment was using Streamlit, Flask, which gives us a good web interface. So these are some of the models that we used for our project and distributed as loan default risk classification model, class stack ensemble model, logistic regression, random forest, XGBoost, Cox proportional hazards model, and K-plan Meyer survival analysis. So these are some of the outputs from the visualizations we trained from our models. We have the univariate numerical features, bivariate analysis. These are visualizations from our dataset. Then we also have a credit score distribution per employment status, monthly income distribution, and credit score versus monthly income. Then now these are some of the outputs we got from the models we trained. And we'll start with random forest, which gave us a mean cost validation score of 94%, which was one of our best models. And these are its outputs, giving us those graphs. Then we also had the K-plan, which was also a good model we trained. It also gave us at least a mean probability of about 70%. Those are its graphs, the K-plan. Then we had the logistic regression. This one also gave us a good mean score after training it of about 70%. And these are its different graphs and outputs. And we have the XGBoost, which was also good, and we trained it, and it also gave us at least a mean score of about 60%. And these are its graphs that we deduced with its important features. We have the Cox proportional hazard model, which we trained also. These were its outputs, giving us that, the ratios, and also it was ranging around 70%. And we have the light GBM, which was also around 68% mean accuracy. Then we have the autoencoder, which was a bit weak, but was also a trained model, and these are the results we deduced out of it. Then we had the sharp. This one is for explainable AI to be able to explain whether why the reason why the person has not been given the loan or accepted. Yeah. So this is our model selection and deployment. This one involves this is how our UI looks like, and our front end, and how the design of the UI looks like, and how it works. So how it works is we have a deployment phase. We capture the deployment developer local environment where we have the code. Then of course we did version control, put it to GitHub. Then we did model preparation. After doing model preparation, we build the containers like Docker to push. Then we of course find our deployment targets using Docker SDKs. Then after we push it to the runtime, and then we deploy. Yeah. Then model compression techniques. We have these are some of the compression techniques we added into our project, and there was knowledge distillation. This one involves regime yielded exception empirical results. This one was just drastically shrinking heavy model with payloads from tens of megabytes, and this was also one of the trained techniques we had. Despite its extreme reduction in size, the distilled student models successfully retain critical predictive capabilities, achieving up to 99.74 agreement rate. So this was for knowledge distillation. Then we had pruning, which was also one of the results we got. As you can see on the right, the graphs we reduced, and in this model, it reduced model sizes by 91% and improved inference speeds by 2.6 times. Its top performer was XGB post-loan aggressive model, achieved a massive 84 times total compression. Then it also had original models which are significantly parameterized. Random forest needed only 75 trees instead of 300. And logistic regression maxed out its accuracy at only 9 of 13 features. Then we had quantization with also its results listed on the right from the model it trained. For it was used to evaluate these 8 models across FP32 and FP16 and int8 formats. Revealed that supervised classifiers maintain identical accuracy across all precisions. Then, of course, gradient boosted trees saw up to 98.6 reduction in size, and also K-means clustering weak results were affected by quantization, and also transitioning to lower precisions like FP16 or int8 doesn't affect classifier accuracy. So demonstration of our deployed product, we have a system workflow and interface where I have the input interface from where loan officers, applicants enter their financial details, insert screenshots, user input form, or Jupyter Notebook data entry. Then there was the processing engine, which involved Python-based back-end running, the deployment classification models like XGBoost. Then we have the output dashboard, which gives the final decision. Then the repayment prediction, which is a yes or no, or probability or default in percentage, explainability plot with sharp or line graph. Then the core IP generated from this project, synthetic borrower dataset. This involves custom generated features. Then we also have explainable AI involving. Then we also have source code and scripts. This one involves Jupyter notebooks. So our limitations were data scarcity and informal income not recorded, then potential bias and privacy concerns. Our conclusions are ML transforms risk assessment, replacing manual judgment with predictive analytics. Synthetic data enables safe, realistic model experimentation. So our next steps will be alternative credit scoring like mobile money behavior, fraud detection integration, personalized loan recommendations. These are some of the references that we had referred to from regarding our project. These are also more of the references that we had. And want to end this presentation by acknowledging the Department of Computer Science, courses, Makerere University, and special thanks to our supervisor, Dr. Galiwango Marvin and Dr. M. France for guiding us throughout this project. Thank you for listening.